Turbofans, like all the turbojet family, rely heavily on the flow entering the engine to operate properly. And in order for the flow to go through into the engine, it first needs to go through the inlet. And while the inlet is always skipped over because it is quite simplistic and somewhat boring in some sense, it has a very important function, and that is if you don't get the inlet flow right, the rest of the turbofan won't work properly. And while it doesn't have any moving parts, at least generally the inlet doesn't have moving parts, it does direct the flow, and as such, its main goal is to make the flow as uniform as possible as it enters the turbofan, as well as be as in line as possible with the turbofan. So the less uniform the flow is, and the less straight it is, the worse the engine's performance will be. And despite it being quite boring, the inlet is actually the first stage in the entire turbofan, so it is arguably the most important because everything after it is greatly affected by the inlet. To that end, it is important to know what the flow looks like as it goes through the inlet and to get it right. And things can get even more complicated when you think about the operating conditions that a turbofan can experience. So turbofans are usually found on airplanes, like pretty much all airplanes from like anything that goes from 500 km per hour to 1500 km per hour. They all use turbofans, whether that's low bypass or high bypass. And turbofans here, they are subjected to a lot of different conditions. For example, the easiest and most obvious to think about is when the free stream flow is directly in line with the engine. But that is rarely the case. In fact, now when you go onto an airplane, there's a good chance that somewhere on the airplane, there'll be information about the weather patterns and the flight conditions that you're experiencing. So if you look at that, you'll see that it is very rare for there not to be some kind of crosswind, even if it is just a few degrees. That means that the flow seeing the inlet is now at an angle to it. So the inlet needs to work even harder to align the flow properly and in a way that makes the flow meet the uniformity requirements of the compressor/fan stage. For those of you who don't know, the compressor stage is the section of the turbofan that is directly behind the inlet. And this is also a very important stage because if you actually go through the mathematics of a turbofan and turbojet family in general, the efficiency of a turbofan is directly related to the compressor and how much it compresses the flow, where the greater the compression ratio, the more efficient the engine becomes. Now, the compressor can only really work well if it has good flow to work with to begin with. And to illustrate what I mean, let's discuss what a compressor is and how it works. So in its most basic form, a compressor is literally just a disc with a bunch of blades coming radially out. And these blades can be thought of as like airfoils, little airfoils coming out all around. Then as the disc spins around, and hence the blades also spin around, they chop through the air and squash it together. That is the compression part. Now, in that basic description, we have just covered why the compressor is so sensitive to the inlet flow, because the blades are airfoils, and we know that an airfoil's performance is greatly affected by the angle of attack of that airfoil. So if the flow is coming in at a greater angle of attack, that is going to make the airfoil either produce a lot more lift or stall the airfoil. And in the latter case, that usually results in the compressor not performing very well. So because the blades, or airfoils if you like to think of them like that, are so sensitive to the angle of attack of the air, it stands to reason that the inlet greatly affects the blade's performance because the inlet controls the angle of the flow hitting the blades. So that is why the inlet is so important and how it affects the compressor's performance and hence the efficiency of the engine. Now, just briefly, let's continue this process to illustrate how the rest of the engine is affected by the inlet and then the compressor and as we go down through the stages. So let's say the inlet isn't performing as well as what it should be. As a result, the compressor can't compress the flow as much, we know that. Okay, so then what happens? Well, the air that goes into the burner section, which is, as the name suggests, is where we burn the air-fuel mixture. And that is the point directly behind the compressor. So as the air exits the compressor, it goes into the burner. We spray some fuel into it, mix it around, and then a high compression ratio results in a cleaner and more efficient burn of the fuel. A general analogy to that is when we have internal combustion engines, so like in a regular car. If we have a high compression ratio in these pistons, we get a more efficient burn. And okay, in a car, we do have an upper limit of the compression ratio, which occurs because if you compress too much, then you'll get an ignition without a spark. And if the piston is still compressing, as happens, it would damage the cams and the piston and even the cylinder. So we see in two different applications, higher compression ratios yield better burns. We release more energy. So coming back to the turbofan and turbojet family, if we have a worse performing inlet, we get less compression out of the compressor stage, which means we don't burn the fuel as well, which means we get less energy out of the fuel. Now the burner is now operating worse. So the next stage in the turbine is the turbojet, sorry, is the turbine, and that is there to extract some energy from the flow to then power the compressor upstream. So the compressor upstream won't really turn unless you actually put energy into it, and that comes from the turbine. So from the burner, we know that we don't have as much energy being released. So if there is less energy in the flow because of the burner didn't perform as well, the turbine can't extract as much energy, and that makes the compressor suffer as well because it doesn't have as much energy to cycle around. So we get this process where things just keep getting worse and worse in this loop. Then finally, after the turbine, we have the nozzle, which is there to expand the flow and to throw it out the back to generate thrust. And the reason why we expand the flow is because we reduce the pressure, so ideally it is about the same pressure as at the back of the engine behind it. That way we get the most thrust possible. If we underexpand it, something known as underexpand, which is where we don't expand the flow enough, we are then not maximizing the amount of thrust that we can get. On the other hand, if we overexpand it, so we expand it too much to the point where the pressure inside the flow is less than the surrounding pressure, that creates back pressure and can affect the turbine's performance because at the end of the day, the turbine is also just a set of airfoils around this disc. Now, the nozzle is designed to expand the air a certain amount. And this is based on the flow and how much fuel has been burnt. So if the burner doesn't work very well, then the nozzle will not perform optimally either, and hence we will get inefficiencies here as well. And this all comes back to the inlet, because if the inlet isn't working well, then the rest of the turbofan isn't going to be working well either. So that is how important the inlet is. And okay, I went into a little more detail into how turbofan works and turbojet works than I planned, but I think it was good because it helps illustrate just how important the inlet is to the engine and why its performance matters so much. So let's move on to what this podcast is about, and we're going to look at how inlet performs at different flow angles and different conditions. So we want to see how uniform the flow is, and to do that we are looking at a paper called, if I scroll up, let's go here, High Resolution Turbofan Intake Flow Characterization by Automated Stereoscopic PIV in an Industrial Wind Tunnel Environment. So this is open access, and you can find the link below. And the goal of this paper from the researcher's point of view was to show that something called stereoscopic PIV could be used to measure the velocity plane and the uniformity in the intake of the turbofan. But while that is interesting from a technological point of view, we are more interested in the actual characterization of the flow in the inlet and how the different flow angles affect it. And I should just quickly say here, if you want to learn how to use OpenFoam, we have a course in the link below. But let's get back to this podcast and talk about what stereoscopic PIV is. I'll just explain it briefly. So it is very similar to regular PIV in that you shine a laser sheet into the flow, and then you put seeding particles into the flow to reflect the laser. Then you position a camera so that you can see the laser sheet from where it's stationed, and the light that reflects off the particles will then be captured by the camera. You then take two quick pictures, like only 20 milliseconds apart, or 10 milliseconds, or depending on how far you want these particles to move in a certain amount of time. This is the general amount of time, about 20 milliseconds or so. And from these two pictures, you can then see where the particles have moved in time, and hence see how the flow is moving in that plane. That is basic PIV. And one general limitation to this is that you can only usually measure two components of the velocity, because you can only see how the flow moved in that plane. With stereo PIV, you can now see the third velocity component, and that is what they are doing here. And that is stereo PIV in a nutshell. And we actually have a podcast explaining that in detail called How Stereo PIV Works. So if you want to learn more about the details of it, you can check out that podcast. But we want to look at this podcast with turbofan intakes. So these researchers want to use this technique to see the flow in the intake. Now let's look at their experimental setup. So they used two ND-YAG lasers, which is the most standard laser type used in PIV. This gives a green laser, which you can then put through some optics to make a sheet of whatever thickness you want. In figure 1, they show the turbofan and how the laser shone in. So let's go down to figure 1. We have this clear, or more accurately, a colorless plastic spacing ring in the turbofan's intake here. So you have the regular turbofan intake. Then at a certain point, they put this clear disc in there around the outside. Then you can shine the laser through there and then make these planes that you can then capture what's happening with the flow. Now in figure 2, we see the test section, and one thing that stands out here is that they have a turntable underneath, and then like the turbofan is on top of that. And I guess this is how they changed the angle of the turbofan compared to the oncoming flow to create a crosswind situation. And they tested this at Mach 0.2 and changed the angle of attack from 25 degrees to 35 degrees in 1 degree increments, which is a pretty severe angle of attack range when you think about it. I mean, 35 degrees is really high. When you think about an airplane taking off, the actual angle of attack of the wings is not nearly as much. When you put the additional flow control devices on there, okay, it changes the camber, etc. The actual wing itself with the inlet and the turbofan is usually less than 35 degrees. So this is quite severe. And although, because the speed is so slow, it is more expected that this is not really like a cruise Mach number for the airliner. This is like 0.2, that's not very high for an airliner. Airliner is more around 0.8, 0.9 Mach number. So this is quite low, but still the same general ideas can hold. And the Reynolds number here is based on the inlet diameter of the intake is 1.1 million, sorry. Now, one thing that I'm really impressed with actually, I was going to say pretty impressed, but I'm actually really impressed, is the job that they did with their uncertainty. So they did a really good job predicting their uncertainty of their measurements. And so given their setup, it is quite difficult to determine the uncertainty of their PIV images, because you not only have the typical uncertainty, but now also additional uncertainty based on how much the inlet flow each camera taking pictures can access because of the constraint with this intake. So in figure 8, if I scroll down to figure 8, they give some pictures, some color plots showing the uncertainty normalized to the axial velocity. So down in this picture here, this is the top line. So generally the bottom and the top left of the inlet produce the greatest uncertainty. So the bottom here and the top left, and that's around 1% uncertainty, which is still pretty good. And so I'm impressed with their setup and uncertainty analysis. Now, one thing I should mention is I'm not sure if this is a 95% uncertainty CI confidence interval or a 68% or whatever, but the fact that they've gone to these lengths, it's quite easy to extrapolate out into whatever you want. But let's not move on to the results now. So in figure 10, we see the velocity distribution normalized to the average axial velocity. So these plots might seem a little complex, but the main thing to watch for here is where the red is. When there is red, it means that we actually have some separated flow, which is not good for the intake. And we see that as angle of attack increases, so it gets higher as we go along from A, B, C, all the way down to G and F, we get more flow separating around the bottom section. So as angle of attack increases, we get more separation at the bottom of the intake. And that makes sense because as angle of attack increases, the flow has to flow over the lip of the inlet, and that is where you're going to get separation. Interestingly though, while increasing angle of attack does increase the severity of the reverse flow velocity, the area that separated flow occurs at doesn't change too much. So you can see here, when we increase angle of attack, the amount of area that we have this red is pretty much constant. The red does change in magnitude, but overall the area doesn't. So let me explain a little bit more. Near the red, we also get a little bit of a change in the velocity. In fact, it actually increases a little bit. So we have the red, which signifies a separated flow. Then just above that, we get a little bit of a bluer flow. So let me zoom in here. And we can see that compared to the color bar, that's actually above 1. So we actually get a higher velocity here just out around the separated flow. So that is changing the velocity and the uniformity a little bit. Now, another thing to note is the uniformity of the flow, as I just mentioned. So we can see that even when there isn't any flow separation because the angle of attack is low enough, so these two angles of attack here, the flow isn't exactly uniform still. There may be a 20% spread in the velocity across the inlet. And when we increase angle of attack, yes, the non-uniformity increases, as you'd expect. I mean, there is some separated flow, so of course there is less flow uniformity, but increased angle of attack also doesn't increase the uniformity in the upper section of the inlet. It increases the non-uniformity. So that's really interesting. And this literally shows just how stable the flow is across a fairly large range of angles of attack. Because you can see the non-uniformity here at the 26 degree angle of attack, I think it was 27 degree, is pretty much the same as 35. You can see that it doesn't change too much across here compared to here. So the separated flow stays pretty constant, as does the non-uniformity. So there is non-uniformity, but it's pretty constant. And the change in velocity is about 50% across this range. So that's quite interesting. If you think about the turbojet or the turbofan, you have one part which is taking in a velocity at, let's say, 100 meters per second or whatever. Then next to it might be 150 meters per second. So there's quite a bit of a change here, just going a few millimeters left or right. And that results in quite a big difference in velocities that the fan and the compressor blades will see, which means that they have to work a bit harder. So that is 4 different angles of attack, and that makes sense because the airplane that these engines would be stuck on would go through a range of angles of attack as it, for example, takes off or as it declines or whatever. So the angle of attack does not stay constant through its operating range. But what about in crosswinds? So in figure 12, we have a crosswind of 15 knots and the effect it has on the non-uniformity in the intake. And in addition to 15 knots, which is a pretty decent crosswind, they also looked at different mass flow rates through the turbojet. And a higher mass flow rate means that the effective angle of attack of the air entering the intake, when factoring in a crosswind, will drop. So interestingly, there is a sweet spot where when you have the mass flow rate quite low, so the engine isn't working very hard, there is a lot of flow separation over the edge of the inlet facing the crosswind, so this edge here, this red here. That makes sense because you have the edge here which the flow has to skip over, and that's where the flow separation will occur. And the non-uniformity is really large, like there's even reverse flow. It goes down to minus 50% of the average flow entering the inlet. So that's quite bad. And we can see that there is actually more in the upper left corner than just across the entire left side. The reason for this, as given by the authors, is that because this turbofan is not actually symmetric, and it is in close proximity to the ground, that is having an effect on the flow hitting the turbofan and also changing where the separation occurs. It's shifting it up. So presumably, if the engine wasn't near the ground or any other structure, and the inlet was actually symmetric, the entire left side would probably see a fairly uniform flow separation where going from the bottom to the top, it would be centered around the center line, not shifted up to the top left part. Now, as the mass flow rate increases, so we go from A, B, C, all the way down to F and G, we see that the flow becomes very uniform, and even with this crosswind, so when we get to D and E, we can see that there's quite a nice spread of velocity. It's not really changing very much. There is one exception though. There is this little eye here, which has quite low velocity. And the reason for this apparently is the formation of a vortex, which we'll cover later on in more detail when we look at figure 14. Anyway, let's move on to greater mass flow rates. So we looked at the very low flow rates. Medium flow rates result in quite uniform velocity profiles. And let's look at higher mass flow rates. So in figures 12F and G, we see the effects of the crosswind of 15 knots at very high mass flow rates through this engine. So we see the engine is operating pretty much at 100%. Now, we get the re-emergence of the flow separation on the top left corner that we had at low mass flow rates. And that's a little bit strange because at low mass flow rates, we had separation, and medium mass flow rates, we had no separation. Now, at high mass flow rates, we have some separation. What is going on here? There seems to be this sweet spot around this middle operating range where the flow is the best. And that apparently has been seen in other studies as well that these authors have mentioned in this study. Now, they explain the reason for this as 2 different mechanisms. So at low mass flow rates, they say that this separation is caused by regular flow separation in essence. They give quite a technical explanation where they say that the separation is diffusion driven and there is a plateau in the isentropic Mach number around the inlet tip, which pretty much means that there is good old-fashioned flow separation here. As the mass flow rate increases to medium amounts, there is no longer this separation occurring here. But pushing the mass flow rate higher to the maximum mass flow rate down here, now that induces flow separation through shocks. Proof of this is given in figure 13, so let's go down to that, which gives the isentropic Mach number going from the outside of the inlet to the inside. And as the mass flow rate increases, there is a continual jump in the Mach number across the lip until it becomes supersonic. And the resulting shock waves induce the separation over the lip. So that's pretty cool. If the mass flow rate is too low, there is no shock, but if the flow rate doesn't have enough energy to stay attached, then it will detach. If the mass flow rate is too high, then the flow has a lot of energy, so it stays attached that way, but the shocks then make it separate. And if the mass flow rate is just right, the boundary layer has enough energy to stay attached, and there is no shocks to make it separate either. So that, I guess we could call the Goldilocks phenomenon. Now let's look on to figure 14 as promised to look into the formation of a vortex in the inlet. So that seems a bit strange, like you have this inlet for this turbojet and this vortex just occurs there. So one thing I should mention is that up until now, we've been looking at average results. We will now look at instantaneous results. So the authors say that the inlet flow is usually very unsteady because of the highly three-dimensional flow and the flow separation. So in figure 14, we have the probability of a vortex forming in the inlet. So remember back in figure 12 where we saw this I in the velocities showing this non-uniformity in the bottom left. Now these probability plots show that the chances of a vortex forming here is less than 5%. And that is with the same 15 knot crosswind we saw earlier. So in figure 12, where the average results showed like a 30% change in the velocity in this range, that's a non-uniformity of 30% or so. And it means that when this vortex is actually present, the non-uniformity is greater than 30% because only around 3 to 4% of the time do we get a vortex here. And even with such a small fraction of time that it occurs, the vortex has such a big effect on the average velocity field. So the vortex that forms must be very strong to alter the velocity field so much. And one thing to note is that figure 1, so let me scroll up to that, shows as the mass flow increases, the probability of the vortex forming increases as well. Oh, sorry, figure 15, I should say, not figure 1, figure 15 here. Let's go down to that one here. So as the mass flow increases from 56% up 34 to 65%, the probability of this vortex forming increases. And that kind of agrees with what we see in figure 12, where going from a very low mass flow rate to a medium mass flow rate results in much greater flow non-uniformity in this vortex region. That means that either the vortex is occurring much more often, or it could be stronger so that it affects the flow even more, or it could be both. I unfortunately don't know what the strength of this vortex is, but I would like to think that it is likely that the vortex is getting stronger as the velocity of the flow is greater, and hence there is more energy to create a feature here as the mass flow increases. But anyway, that is speculation. So let's move on to figure 15, where we have the probability of the flow separating in the top left region with different mass flow rates. So for very low mass flow rates and very high mass flow rates, these probability plots pretty much say that there's a 70% chance or greater that it will form. So 70% of the time or more, we do get separation in this top left part, so almost always. And interestingly, at medium mass flow rates, so this middle plot here, we didn't see in figure 12 any real signs of flow separation. So if I go to figure 12, there wasn't any flow separation around this region here in the top left. But figure 15 says that there was some of the time, but really just tightly hugging the left wall. So I don't know, I would have thought that even at this level and location of flow separation, they would have produced some visible results in figure 12, but apparently not. So let me know what you think about why that's happening. And what do you think figure 15 is showing? Why do you think it's showing some flow separation here? But figure 12 doesn't show any flow separation, even though it's transient compared to average. The average should still be affected by the transient results. So I'm not sure why that's occurring, and if you have any ideas, let me know in the comments below. And with that, we come to the end of this podcast. I found it really interesting because while turbofans and turbojet families in general are greatly affected by the inlet flow, the inlets are not perfect. And there are some situations that do occur in real life where there is a little flow separation and even a vortex being ingested. On the other hand, this particular inlet really stabilized when changing angle of attack. So we saw that increased angle of attack across a 10-degree range didn't have much of an effect on the uniformity of the air coming into the turbofan, which means that the turbofan can operate fairly consistently under quite different operating conditions. So that is the end of this podcast. If you'd like to, make sure to like it and hit the subscribe button or follow button, whichever platform you're on. And did you know that your experiments, like most aerodynamic experiments, probably have a 2 to 4% error in them that you aren't even aware of? And we make an instrument called the Atmosphere Hawk, which gets rid of this error for you. And if you want to learn how and why this occurs, we go through the math in the link below. And if you want to learn how to use OpenFlame, which is an incredibly good and free CFD software, but it's hard to learn, you can take our course in the link below and make it a lot easier on yourself. So that's the end of this podcast. See you next podcast. Peace, amigos.